in the secondary mission, we had better results. It was much more fruitful than the first one. Of course, there isn't any ongoing fire at the moment, so we didn't really use the capabilities of the camera for that purpose, but we also used the visible light camera so as to determine whether the area we filmed using the CanSat camera could be prone or susceptible to certain geological disasters. For instance, fires. Happily, we didn't quite get to the conclusion that fires, catastrophic wildfires, would be a problem in this region, because as you can see in these pictures here, this area is made up of very bushy and sparse vegetation. It's also a plain, meaning it's accessible, and it's also close to the sea. And it's also very far away from the population, meaning it wouldn't be really very dangerous. Here you have some of the photos we also captured.
As Pedro said, we were able to determine the average speed. The video granted us with the duration of the fall, which was 1 minute and 32 seconds. And the graphic gave us the initial height and the distance it traveled, which was 934 meters. So we were able to determine that the average velocity was 10.2 meters per second, which was within the expected. The equipment we used to receive the live footage was the RC832 5.8G AV receiver with an each-Einstein pad, and the USB EasyCap video adapter, which converted the radio signal to video, making it possible to watch the footage on the computer, which was filmed by the each-1000 TVL camera.
Now, talking about our possible improvements. We could have had more rigorous testing. Like, for example, we should have tried our concept in more similar conditions to the real launch in order to prevent last-minute failures or even unforeseen problems. Next time, we must also build another ground station or even another CanSat to have a backup plan to any problem. And we should have also optimized our power consumption, like, for example, using another battery or even using another component.
We could have also had backup components and devices in case others failed, which would allow us to deal with critical flaws and equipment replacement. On the other hand, we could have also programmed the buzzer in a way that it would turn off each time it reaches a certain limit, rather than just keeping it on all the time reducing the power consumption.
We could also have used an SD card that would make data loss much more unlikely. We could also test various parachutes to determine which one would be more stable and provide better camera footage. We could also have chosen the best antenna to provide for our goals on this mission.
So here we have the live footage of our camera, and to conclude, even though we weren't completely successful in our endeavor, as our CanSat suffered heavy damage and we weren't able to complete our primary mission, the achievement of the live video footage still edged us closer to our goals, and this experience was extremely rewarding, for which we would like to thank you all.
No.
First thing you said that you were kind of taking the provided to you by the sanitary team. So that's what you were missing from the right? Because they didn't have the initial part.
Esta equipa está sendo levada, mas eu posso colocar. Quero fazer os passos com o ar, mas esta vai ter que ser levada.
And when it got to the ground, you also didn't receive any data. So you just had that 1018 hectopascals to be sure that you were getting the right value for the zero, right?
Yes.
Okay.
Any more questions?
Any other questions? Yeah.
Your initial project was to use infrared imaging, and then you switched to TV imaging. And why was that? And would you be able to test the existence of fires using this kind of image? And with what success? What do you expect?
But using an infrared camera to detect fires.
Or using the one we used.
Actually, you have used just a TV camera.
Yeah, normal camera.
Well,
yeah.
for two reasons. First of all, it's just logistics, because we didn't really have the time for an infrared camera to be sent to us from China. It would take like 3 months. We also tried to convert a camera into another camera, because there are ways in which we can convert this into an infrared camera. But it would be a very low resolution camera, so that's why we didn't do it. And the second reason is because it would also allow us to limit the areas according to their geological characteristics, because using an infrared camera it would be harder to do that. So visually it would be easier for us to analyze the place we are filming, so as to determine whether it would be more susceptible to disasters.
Is the data plot from your data? Is that your data?
No, it's other team.
Okay, thank you very much for your presentation. We move now to the J4R3 Sati. Please, Camilo.
From Marinha Grande, Leiria, or does it? No.
Hello, I'm Francisco, and I'm the responsible for the prototyping of the mechanical structure.
I'm Guilherme, and I'm the responsible for software programming and component selection.
My name is Anaísa, and I'm responsible for the data handling, documentation, and parachute.
I'm Beatriz, and I'm the responsible for the data handling and antennas.
I am Diogo, and I'm responsible for the dissemination, communication, and financial management.
My name is Antonio, and I'm responsible for programming, electronics, software, and telemetry.
First and foremost, we'd like to admit that our project organization was not always done in the best way, since our common platform of information and documentation was not always well organized, but has contributed negatively to the success of our project. Nevertheless, we worked very hard, always attempting to reach wider horizons and new horizons, and we have a great determination that was never affected by these beginner mistakes. However, our work was severely affected by the way we faced major errors that we didn't overcome and that turned our microsatellite into a dysfunctional one.
Because this mission was quite ambitious, we for a team who was participating for the first time. We didn't complete the test the organization recommended us to do with the sensors and the satellite. And obviously we had several problems. To fix those problems, we made voltage tests. We also checked every connection on the printed circuit boards, and we also tested some sensors individually, but we didn't come with any conclusion.
So this is our analysis software. It's called processing. We coded the software so it can we can get this interface to show us the live data the satellite sends to us. But because of the fact that the satellite wasn't able to transmit with telemetry the data, we couldn't watch anything. However, if the data was sent to us, we would hit that button there that says rec, and it will save all the data, the live data, and we could open that data with which is a CSV file in Microsoft Excel for further analysis.
In what has to be with the external structure, we had no problems. Also, all the components were tested in a test board, electronic test board, but we had no time to test them into the volume.
Parachute, and I must say, it was a success. It was a success. I was afraid it wouldn't work, and after the first day when we tested, the cards get tangled, but I was able to solve it, the team was able to solve it, and it was a success. But further tests in another project we'll have to improve because it could get more stable, as well as our casing. The hexagonal perforation should have different rotations for the fractional plane to be different, so it wouldn't actually broke, but it did broke, but it was okay because our cockroach was safe.
Now I will talk about temperature, pressure, and humidity gradients. These graphs are all about the fall. It's only during the fall time that we start. Here you can see in the right the expected results, and on the left we have the results that were obtained. On the temperature gradient, you can see that here the trend line, the main line, is really close to the one on the expected results. For the pressure gradient, you can see that it has this exponential graph that is really close and similar to the one that we expected. The humidity was created by main values which were between 63 and 71%.
Now about the cockroach, yes, she survived the impact on the ground, and now she is alive, and she's right on this glass, the Christiana. Unfortunately, she lost her leg and her antenna, so it was pretty bad, but she's still alive. We also recorded live the different fall phases that we can see on this video.
So, did the main mission and the secondary mission go as you planned? For the most part, yes. Well, the cockroach is there. It's live. We got the video. It actually survived. We got all the data, the temperatures, everything was sent with it. But, well, there were some setbacks, of course. The satellite, the structure sort of broke down a bit. Not much. What else? The antenna as well. We had a bit of a problem during the test. Our antenna didn't work, but the night before the last one, we built an entire new antenna, thanks to Giuseppe. It's a lot. About 3 hours, we built an antenna. It worked perfectly with duct tape and all. So as you can see, the cockroach there in the video is moving. It's sort of, the quality isn't that great, but well, you can see the legs moving. Also, the satellite didn't launch on the first, because it got stuck on the little tube. So we had to launch it, which you've seen here in the video. But, well, on the second launch, here it is. of selling. It didn't keep on going when the satellite hit the ground, which is a mistake, a mishap. That's what up. It went on pretty well now. That's my work too.
When I was talking about pressure, humidity, and temperature, I forgot to talk about O2 and UV values. They were mean values. So the O2 were between 19 and 21%, and UV was about 19.5 watts per square meter. Philip.
To conclude, I believe it is relevant to mention that regardless of the mistakes we may have made and the inconsistencies of what we had expected to be the results, we still acquired results that we were expecting. And the conclusion was pretty much what we had presumed before we had started the launch. Also, we also believe that it is relevant to mention that aside from the conclusion, which was what we desired, just the fact that we got to work in this project and all the developments and things we've learned throughout the whole process are certainly have become something that we value and that we know that in the future will reveal themselves as being useful. We'd like to thank every one of you, the institution, the CANSAT, who made this project possible. Thank you.
Close of the dipole element that made the signal to be barely received. However, we had solved the problem by removing that director, increasing the quality of the signal received by our antenna.
Initially, we made two parachutes, which are circular parachutes made from a single piece of fabric, which revealed to be inefficient. So we decided to craft a semi-ellipsoidal one made of 12 pieces of fabric sewed together, which also include a cord with a breaking strength of 22 kilograms. We also added some pieces of fabric to decrease the pressure on the nylon. We calculated the measurements of our parachute based on the website on the top. However, we used a really wrong value of the drag coefficient, which led to our parachute to be oversized. This fact contributed to our parachute to be carried away by the strong wind.
Finally, we like to assert that even without mathematical or physical results, there is certainly
Alguém que eu leio. Talvez tu. Na mão. Não queres ficar aqui, fica.
Porque não? Se calhar melhor.
Hello, this
This is our project. It's a seed release system prototype according to environmental conditions.
So, the scientific objective of this mission is to use the CANSAT as a prototype that has to be capable of autonomously collect, analyze and interpreting data during the flight, in order to decide for itself if the necessary and sufficient conditions are ensured and make the decision of releasing or not the seeds. This prototype can be adapted for all types of planes, but only endemic plants of the regions or that have been growing there for a long time. And then we choose 3 species to study because of their resilience to fires and to another afforestation and reforestation projects, and because of their distribution in Portugal. Like you can see in the maps, Erica azorica is distributed in all islands of Azores, and the other 2 species are distributed in Portugal continental. Erica azorica was the plant that we used in theory in the final. And we made some gaps for humidity and for temperature based on data from climate, and you can see in the graphic in green is the humidity, and the lower is around 60%. About temperature, in red, the maximum observed was around 25, and the minimum in blue was around 3 degrees, 4 degrees. About CO2, it has to be under than 415 because of we don't want to liberate the seeds during a fire.
So during our launch, we tried to receive data from our satellite, and this is what we have had. So we didn't receive as much data as we hoped, but this was this graphic of the pressure, which is shown in blue, is the data that we've received during the flight and during the fall. And at red, you can see the values that our satellite emitted, because it was able to, for itself, measure its own height. So we achieved these values, and therefore you can see the relationship between height and pressure. We also obtained, as part of our primary and secondary mission, values of the temperature, and you can see that when the satellite was released to the outside of the launching module, we obtained a lower value of temperature, which was much closer to the air temperature, and as shown in the blue color, the temperature observed in the region was within the wanted parameters to release the seeds. And this was some of the values that we've obtained. And as you can see, we were supposed to get data from pressure, temperature, height, and also humidity.
But as you can probably see, the humidity values are pretty wrong, and they're in percentages. This was due to some technical failures with the DHT-11, which was supposed to measure humidity, but it was poorly connected when assembling it at the final launch. We also used the pressure sensor, the BMP-180, and some other problems we had with the CANSAT were that the ground station Arduino stopped working when we arrived at the source, and we had to replace it, thanks to the GSAT team. And finally, the carbon dioxide, which we were supposed to measure with the MK135, we didn't, because due to power restraints, weight restraints, and finally because we couldn't calibrate it well enough after some studying.
We used this Yagi antenna for the launch. Unfortunately, it didn't work as we planned, we only received about 17 sets of data, with only 2 of those being from the descent. Our CANSAT design has a system which releases the seeds with a rotating of the arm of the servo motor. We had some problems with the design because the day before the launch, 1.5 broke, but we solved this by using half of the can set using the can set from the test launch.
Regarding to our recovery system, our final parachute has the same size as the test parachute. So, as we expected, after the test of the recovery system, it was a success because we recovered the can set with no damage. The other part of our recovery system was supposed to be the radio beacon. We wanted to connect an antenna to a SDR software-defined radio, connected both to the tablet with the SDR Touch app. Through it, we were supposed to receive radio waves emitted by the CANSAT after its landing, in order to localize it as quick as possible.
To finish our presentation, I would like to thank all the companies involved in the organization of this event, and I would like to thank as well all the supporters that helped us throughout this project, such as teachers from our school, the teacher that brought us here, and Sementes de Portugal that provided us the seeds for the experiment. I would like to thank as well Mr. Cardeira and Fernando Afonso, who are two experts who helped us a lot. Thank you for listening.
We didn't use seeds, we used sugar, but the seeds weren't released. Weren't released because we didn't have the values from humidity, and in the programming we have the ifs for temperature, humidity, and that's why they didn't release. But we asked to the pilot, the humidity was about 40, so with the temperature that we have, 21, 20, the temperature was very good, but about humidity was very lower. We stipulated 60%, so in these conditions the seeds wouldn't, yes, they...
It was the data we've shown here. It was received by us. There were only 17 data sets received, but we received.
I had the impression that I visited you during the pre-launch campaign. I had the impression that you are not complete many of the tasks. So your preparation, it was not complete. So you needed more time to do it.
We actually had some functions during the...
This is part of the campaign.
Yes, exactly, but almost all of it happened while we were here. And we did fix most of them, but we couldn't do all of them in such a short amount of time.
My opinion is a very nice project as well.
Thank you.
Can I ask just one short question? Yesterday in the afternoon you were saying that you would be trying to estimate the descent velocity but using the video and taking the time from that. Were you able to do anything?
Just because the camera's battery basically vanished during the footage, and we didn't have the whole video of the. We tried it, but we weren't able to understand the time.
Anyway, congratulations for all the work you have done. Thank you.
Next presentation, Sat 3.
Starting with our primary mission, we were able to measure the variations in temperature and pressure. The variations in temperature were not very conclusive. However, the variations in pressure were very conclusive. As you can see in the graph on your right, the pressure values start to be constant when the plane was still in the ground. They start decreasing as the plane took off, and they stabilized when the plane reached a certain altitude and stabilized. When the CANSAT was released, the pressure rapidly increased as expected. Using our pressure values in this formula, we were able to calculate the altitude and create this graph. As you can see, the altitude starts at 0 when the plane was still on the ground. It increases as the plane took off, and of course it decreases very rapidly as the CANSAT was released. This section of the graph will be further on analyzed in more detail by my colleague Andre.
Now, looking at this graphic of acceleration and altitude at the same time, throughout time, which starts a little bit earlier, so you can see very interesting results. At the beginning, both values are around. The first value of altitude is at 0, and the acceleration is stable at 1,000 milli-Gs, which is the gravity acceleration, because the plane is standing still. When the plane starts to do its taxiing to the runway, the acceleration values start to vary a lot, but the height is still at 0. When the plane lifts off, the acceleration varies a lot, and the height increases. With a drop of the CANSAT, there's a big leap in the acceleration that then stabilizes due to the parachute's effect, and the height decreases very rapidly.
Using the graph from altitude, we were able to calculate the average velocity of our CANSAT. It was of 10 meters per second. It is visible that there are 2 slumps during the descent. So we divided the velocity in 3 different segments. In the first segment, using linear regressions, we calculated to be a velocity of 9 meters per second. In the second one, about 7 meters per second. And the last one, the terminal velocity, is about 8 meters per second. We use linear regressions for calculating all these speeds. We believe that our secondary mission related to the landing gear was successful because it was released during the flight and didn't take any damage while landing. As predicted before, the landing gear was released when the parachute soaked. Then the 4 stems occupied their final position, forming a second quadrangular pyramid, and they were kept like this due to springs tension.
Looking at our CANSAT design, we have 3 different pieces. Our main piece in the middle, which you can see on the right, and also in greater detail on the left, is our control module. This holds room for the Arduino, for the buzzer, for the 2 LEDs, for our accelerometer, and also it has various holes for wiring to the other parts, and finally our Falcon tube, which holds our flies. All of these supports hold very tightly the pieces so they can sustain the fall. This is then connected to the landing module below, which also holds 4 AA batteries for power supply, and the inner part of our landing gear, and finally you have the lid on the top. Electronics-wise, our mission was also a great success. We managed to recover data from turning on the CANSAT to its falling and touching the ground, proving the functionality of the Arduino circuits, and also the control module, which managed to keep everything in place, our antenna, and finally our parachute, which made sure the accelerations wouldn't be too big, and also as the calculated terminal speed was correct.
The other secondary mission that we had was to evaluate the effects of the flight on Drosophilus melanogasters. To do that, not just on the short term, but on the long term, we conducted a study of the effects of high acceleration forces on Drosophilus melanogasters. To do that, we submitted them to different conditions. We used 480 Drosophilus melanogaster, being that 60 of each gender were submitted to a different condition. We used 1 G, 1,000 Gs, 10,000 Gs, and 1,400 rotations per minute. After that, we tested on the long term their locomotion and life expectancy. To do the life expectancy test, each 3 or 4 days, we counted those who were dead and registered them on an Excel. The locomotion we made each 30 days. We hit the tube on the desk that they were on, and they naturally tend to climb up. With that, by recording, we could stop the recording and then analyze where they were relatively on the tube. You can see here on the video, I think. No? Well, moving on, we can evaluate where they were and how much they climbed. The tube had 4 centimeters of climbing, so dividing them by sector and estimating that each fly on each sector had climbed half of the distance of each sector, we could estimate the distance covered per fly per condition. With that, we obtained our results.
So moving on to the results, during the fall, the maximum acceleration that we got was 2.16 Gs. According to the study that we've made regarding the life expectancy of the flies, and with that initial acceleration, we can assume that the flies which were on the CanSat, the males would live up to 75 days and the females up to 85. Still looking at these graphics, we can see that the females are more sensitive to high accelerations in the beginning. However, in the long term, they tend to live more than males. Now, the locomotion tests regarding the Gs. At day 0, if we look at day 0, we can see that the groups which were exposed to high accelerations were slightly bit more active than the control group. At day 32, the female groups which were exposed to high accelerations were already slower, and at day 60 they were pretty the same, and we can say that it was caused by the aging of the flies. The males are all equal, so we can say that the males aren't as affected as the females, and yeah, they weren't as affected as the females. Now the rotation per minute results. Although it was a different test with different machines, the results were pretty similar to the Gs, to the G tests. And now the launch tests, the tests that were made on the flies which were under our CanSat. These results were pretty interesting because we could see an unexpected excitement of the flies which caused them to climb up more. Facing these results, we came up with an hypothesis, and we said that we can say that this excitement might have been caused by the combination of some factors, such as the vibration of the plane, which is related to our RPM tests, also the Gs, and other unstudied stimulus, such as the light or the sound that, as we all know, also affect multicellular organisms.
Regarding the dissemination of our project, we created our own Facebook page and on our own website, which we strongly advise you to visit us. All in all, our primary mission and secondary mission were both accomplished as expected. Thank you very much for your attention, and if you have any doubts.
As we said, these data was inconclusive, and I think we can safely assume that although the temperature was supposed to increase with the drop in the height, it actually decreased, and this probably stems from the fact that because our temperature sensors was in the middle of the electronics, it actually got into a higher temperature than the actual surrounding temperature outside, and this made it be a lot heated up when it was inside the plane and when it was dropped. And because the can had holes for the air to come in and actually stabilize the temperature, it had quite the opposite effect because the can was actually hotter than outside. It actually decreased its temperature because the sensor wasn't very well placed.
And what can you say about the final variation of temperature when the campsite is dropped? Do you believe that this is a good measurement, or are you actually measuring the air temperature or not?
We believe it. Yeah, this wasn't the best way of censoring the air temperature. So, yeah, we don't like it.
The thing is, I believe that this is a very good result. I mean, if you look at the time when the CanSat was dropped, the temperature is, oh no, it's decreasing. Sorry. Oh, wrong. I'm wrong. Yeah, it should be going up. It should be going up. Yeah. Okay. Can you show me the descent velocity, the descent speed plot? Yeah. In the middle sector, you have just 6.5, 6.6, and you commented that the global average is 10.2, which is within the parameters. Did you come up with an explanation for these sudden drops that you saw there?
Yes, we have one possible explanation, which are wind currents at certain altitude. That could be wind that could have dropped the CanSat with a higher speed than the normal one.
Okay, my final question is, since you have very good results, show me the plot of pressure versus height, not versus time. We didn't do that. Yeah, you didn't make it, I guess. It would be very nice to see how the pressure varies when you go up in the atmosphere. All your plots are versus time as the mission is going on. But in order to test something, we would need to have variation of pressure as you go up in the atmosphere. That would be the final very good result for you. Okay?
We didn't directly compare it, even though we did make sure all graphics had the same time measurement. If you see, so this would even though they're not directly comparing the same graphic, I think you can also correlate them while you see them, just to make sure that this would be possible.
Don't understand the final value gave, which is the acceleration when it hit the ground of 2.16 Gs, because looking at your plot, I don't see the 2.16 Gs.
That was the maximum.
I see 1.4, something like that. Where did you come up? How did you come up with the 2.16 Gs?
So that is the maximum value achieved in the higher peaks. That was the maximum value achieved during the fall.
Oh, but that was due to vibration.
Yes.
Yeah, and when the can hits the ground,
We lost contact at that point. We lost the contact with the can, but we can assume the value was maybe a little bit higher than the 2.6 Gs.
you could have calculated that because you knew the speed. Yeah, okay. Very nice.
Short one. Which axis is this acceleration from?
So this is the module of the acceleration. So we join all three axes and make.
Just one comment. I think really you did a really nice presentation. You are very cooperative, and I think that I think it's really consistent. You are consistent. You have answers for the questions. You are very consistent in your answers, and I really appreciate your presentation.
Thank you very
much.
Thank you very much.
Já partiste isto.
Good morning. We are Space Info team. We are the team from Azores. We are going to present to you our mission report. So here is our project overview. The sensors transmit to the T minus, and the T minus communicates with the transmitter that communicates with two antennas that are connected to two ground stations. Each ground station will process the same data but focused on specific data. We use the two antennas. The frequency that was assigned to us were 434.16 megahertz. One of the antennas we measured the gain from 4 to 5 decibels. The other one we didn't measure, and the distance they could work at a distance of about 2.2 kilometers. They worked they communicated with the plane when it was the furthest away from us. So our primary mission was gathering data from temperature, pressure, and humidity. We expected that when the CanSat gained altitude, that all of the mentioned before would decrease. Now this is where things started going badly. Our mission lasted about 5 minutes. That was from takeoff to when the plane was circling around. We lost communication when the plane was still gaining altitude. But we still gathered some data that was from the takeoff. As we can see, the temperature rised because it was inside the CanSat. It started heating up, but when it started going up, it decreased because when with more altitude, the less temperature. Pressure was kind of constant. We can't take much conclusions from it. And the humidity dropped since the CanSat was ascending. So where did we fail? We failed on transmission. We came to the conclusion that the radio frequency transmitter didn't work so well. We analyzed all of our CanSats, the power, the sensors, the microcontroller, the programming, everything was working fine. But and we came to the conclusion that it wasn't transmitter. And the CanSat wasn't released because of the parachute. It was stuck on the hatch on the plane 2 times, and the third time up team landed their parachute, and we succeeded in dropping the CanSat. So our secondary mission was the detection of open dumps and detection of water zones. We expected medium values of humidity of around 60%. Humidity is the evaporation of water, so the more heat on the water, the more evaporation, therefore more humidity. And we expected the low methane levels of around 1.7 parts per million. That is the medium value of pollution, methane levels on the air. We gathered data. We gathered the data we received were analog values of from 0 to 1023. We converted. Our medium values were about 30 analog values, and we converted these values to 1.7 parts per million. We did this using this formula. The received data would be converted to parts per million. So here are the graphs of our values. Humidity dropped since the CANSAT elevated, and the methane levels were around 1.7, around the normal values. So we didn't detect any pollution, which was expected. What improvements could we make? We could gather better sensors. The MK2 sensor isn't the most precise sensor, but it was good enough. It is good enough for our purpose. We would resize our parachute. It was too big. It was too compact on the hatch, so it was stuck. A more efficient transmitter, it was our main problem. And real-time graphics. When we were on the mission, we wanted to receive the data, and it would be converted to graphs on real time. This is the application. It was programmed by Luis. The data received would be saved to a text file and converted to this graphs that will show in real time. Before we end, I want to thank all of the organizations that made this possible, and the UP team for lending us their parachutes. Thank you so much. We did, but we lost communication mid-flight.
You added a storage report?
No.
Only to the downing?
No, we didn't gather data from the downing. We just gathered data from the takeoff and when it circled around one time.
Okay, just one thing. This is a remark. When we talk about antennas, we will not talk about distance.
Okay.
Antennas and distance they are not matching. Okay. So gain, yes. Distance, no. Distance depends on many factors, including the way you are operating. Okay. This is just a remark.
I would also like to say that you did a very good analysis of what happened. So with adversity, you now analyze what has happened, what to be improved, etc. And I only think that you cannot take any conclusions about temperature. Can you show again the graphic of temperature? Because it's a heavy side or something. So right at the beginning, there's a discontinuity. I think it's an artifact from the sensor because, yeah, like that.
So the temperature was normal, but when the circuit started heating up and the temperature rised because of the circuits inside the CANSAT, it was very compact. So when it started elevating, when it was already sometime in the air, it started descending. We didn't measure any decimal values, only unities. So it goes from 24 to 25.
Can you show the next plot? I guess is next. So your humidity value, was it good or not?
I think it was good.
Yeah, you should stress that.
The
Mission was a success. We have humidity above the Azores Island. I mean, this was a very good stuff. Yeah, and the methane value was also okay. The problem is the sensor. You were doing some linear transformation in order to get a regular value. I mean, this is nice work, although I would not put too much emphasis on believing the value, but you did some work, and congratulations for that.
Thank you.
Congratulations for that.
Okay, thank you very much.
Thank you.
After him, the next.
Good morning. We are Alpha Robot team from Lisbon. Good morning. We are Alpha Robot team from Lisbon, and we are representing Escola Secundária Zé Gomes Ferreira. As you all know, we have a joint primary mission that consists in measuring the air temperature, atmospheric pressure, and using telemetry transmission. So for our secondary mission, we decided to combine chemistry and physics, trying to study phenomena from both subjects. For the chemistry component, we built and analyzed the emission spectrum of the sun. For the physics, we decided to study the acceleration and the impact force. Furthermore, we drew a 3D trajectory of the can to help its recovery. We would like to emphasize that our objectives are only technical.
The mechanical design of our can set was pretty similar to the sketch. We stored our force-sensitive resistor under the 9-volt battery on the lowest compartment. In the middle compartment, we had a rectangular circuit board with all the components. And we also had to include a 90-gram ballast to make sure we reached the weight goal of 330 grams. As for the top of the can, we planned there to be a external GPS antenna, which we did not include because it didn't fit the can as we expected it to.
As for the software system, we programmed everything using Arduino and used PuTTY to export the data into Excel, where we organize the charts.
As you can see, while the altitude decreases, the pressure increases. Atmospheric pressure is the cause of the gravitational attraction of the planets on the atmospheric gases above the surface. So during the can's fall, when the altitude decreases, there is more overlying atmospheric mass, therefore a higher pressure. The velocity that we calculated was approximately 10.5 meters per second.
As you can see, as the altitude decreases, the temperature decreases as well, but this shouldn't happen. This is due to the fact that the temperature is measured inside of the can and not outside. The temperature inside of the can is higher than the expected because of the overheating of the system. As the can falls, the temperature decreases, trying to achieve a balance with the temperature outside of, so the temperature of the air.
Okay, in this graph we can see that there's a discrepancy between the values obtained from the GPS and the altitudes calculated using the hypsometric formula. For this formula we obtained the sea level pressure value from Instituto Português de Mar e Atmosferas daily weather feed on Vila do Porto, and the discrepancy can be caused by many reasons such as sensor inaccuracy or the loss of packets during the transmission.
Now I am going to talk about the chemistry component of our secondary mission. Here we have the solar spectrum in comparison with the black bodies. The smooth curve is the spectrum of the black body. The two curves match well enough that Sun can be considered a black body for most purpose. For the visible radiation, the black body spectrum is very close to a quadratic function. Here we have the data we received from the can. We drew a quadratic regression, which represents the black body solar spectrum. Then we have the data we received that achieved the atmosphere. These irregularities represents happen due to the backscattering and the absorption in the clouds, as well as the absorption of caused by the oxygen in the atmosphere. All the irregularities should be placed below of the black body spectrum. However, as you can see, they are not, due to the fact that our sensors were not the best for the purpose of our mission. One of our goals was to draw a 3D trajectory of the CanSat during its fall to help its recover and to see it. And we did it using GPS and also Google Earth.
In this table on the left, we have the x, y, and z acceleration values. Sorry. During the fall, but since the can was oscillating, there was no way to determine the resultant force. Although the values seem random, there is a tendency towards the acceleration value of the z-axis to be around the gravitational acceleration. As you can see, that's 10. Oh. As you can see, that's 10, and that's about the gravitational acceleration value in meters per second squared. Sometimes the acceleration values for the z-axis exceed the gravitational acceleration due to high wind speeds pushing the CanSat down. The impact force we detected was 6 newtons, which wasn't the data value we expected.
We had some problems related to secondary emission with the solar spectrum. We ended up using CIST photoresistors, LDR, that gave us a response of the wavelength we wanted to determine. This is a sensor which is very limited but also quite simpler. Furthermore, the LDRs are similar but not exactly the same. So for the future project, we would like to use another sensor which is more suitable, like digital luminosity light sensor with 6 diffraction grating. Each filter would give us different wavelengths. Contrary, this sensor has the same response for the whole spectrum.
Another problem related to our secondary mission was the data supplied by the GPS. Even though the longitudes
and latitude of the data were really close to reality, the altitude was not. We wanted to use that data, the altitude data, to confirm that our calculi were correct, but we couldn't do it.
If we would change anything, we would add a SD card to the CANSAT to memorize the data if the telemetry failed. We would also add another ground station to ensure the capture of the data. Regarding the recovery, we would add a buzzer.
We were really pleased with the amount of results we got, as we got to receive results all throughout the fall of the CANSAT. Because of this, we were nicely surprised with the quality of the telemetry.
To conclude, it was a pleasure for us to be a part of such a well-organized competition here in Azores. We were able to learn more about programming, electronics, and engineering, also while having a glimpse at the small space mission. Thank you.
Interesting. Only one. Okay. Show us the plot of the spectrum that you collected. This is the first time we see someone trying to measure the solar spectrum. Would be nice for you to include, no, the previous one. Go back to, yeah, that one. What is the width of the spectrum range for all the filters that you used? You have put very narrow bars. I would like to know if the blue line overlaps with the green line, if it overlaps with the yellow line, or were they, and I'm going to put the technical designation, are they narrow filters or are they wide filters to get a broad range of wavelengths?
Okay, we covered each sensor with a cellophane paper. We used the colors yellow, red, green, blue, and violet.
Yeah, okay, but you don't know how many wavelengths, how many angstroms, or...
No, we know the extremes, but no, we don't know the exact, the wavelength of...
Violet was what? Violet was also cellophane?
Yes.
Okay, so you try to fit quadratic curve, and why was that? Because you said that the Planck function is well defined by a
Yes.
parabolic function.
I'm going to go. Yes, here we have the solar spectrum in comparison with the black body spectrum. And as you can see, in the visible radiation, they are quite similar, and that is why the sun can be considered a black body. And the black body is similar to a quadratic function, and that's why we decided to do that.
Okay, very nice. The final result is not so good, but congratulations
Yes.
for that as well. Really
Thank you.
Congratulations for the work you have.
We tried because the sensors were not the best.
Yeah, they were not.
They're not the best for the purpose.
Well, just only one question. In the beginning, you said that your objective is only technical. The technical objectives in your project. Why do you say this?
We are not trying to study the sun. The sun is already studied. We just want to try to analyze and trying to replicate what is the solar spectrum. That is why. I don't know if I'm making myself. Okay. Thank you.
Okay, thank you very much for your presentation.
Okay, thank you.
So we are a WuzoX team, and the object of our CANSAT was to investigate the potential of microsatellites as reliable samplers for airborne microplastics research. For our primary mission, we used the Arduino of the original CANSAT kit, and despite of the good results in the lab and field pre-tests, our microsatellite could not complete the primary mission. After the launch, we made a research of what could have gone wrong, because everything was working at the morning of that day, and 5 minutes before the launch, when we disconnected the Arduino from the computer and we connected it to the 9-volt batteries, it simply stopped working. And when we connected again to the computer, the code was not running. So we put an hypothesis that Arduino could not store the code. So we made some research, and we checked the solders and the connections, and we checked the tensions of all sensors, all components, the battery, and the Arduino. It was everything okay. We deconstruct the entire circuit so we can test everything at Promenor, and we searched for help of specialized people, some teachers of other teams, and a member of the jury. The member of the jury suggested us to install a driver for the Arduino Pro Micro. We were using the driver for the Arduino Leonardo that was recommended at the CANSAT kit. We used it, but it still didn't work. It has the same problem. So as the last resource, we ran a blink test in the Arduino, and it worked either on computer and either on the 9-volt batteries and either on others' computers. So we built another hypothesis that when the Arduino was performing a simple code, it would not have any limitations with the USB, because we know that can be some restrictions when using the USB, and with some more complex functions of the Arduino Pro Micro, as one member of the jury told us. So now our secondary mission.
Well, on the other hand, the secondary mission was quite successful. We can see on the up and left the results that we had on catching microplastics. We can see that we had no contamination, because we have footage that the parachute fell closed, and the 9th and 10th filter had no microplastics, no particles at all. We also researched some scientific papers on the issue on airborne microplastics, and we found some mean values. You can see that the fibers on outdoor air is about 0.3 to 1.5 particles per cubic meter. And you can see that 10 to 30% of total particles in microplastics are from 0.5 millimeters to 5 millimeters. We couldn't categorize the particles that have less than 1 millimeter, because we needed a microscope with 1,000 magnifier lens, 100 magnifier lens, to have 1,000 magnifier analysis. To calculate our mean values of the quantity of fibers on the outdoors air, we had to calculate the volume of the air cone that the parachute went through. We calculated that by using that formula. A is the area of the filter, and F is the number of filters that we used, and D is the distance that the parachute went through. We did a range because we don't know what the distance is precisely. So we did a minimal distance, that is a vertical fall, and we did a max distance that was from the vertical fall landing to a 2 kilometer distance was 2 kilometers. So that way you calculated the two volumes, 30.2 cubic meters and 11.8 cubic meters, and then we calculated the delta. That is the number of particles, our number of particles per cubic meter. So we calculated that by having again a number of filters and the mean value of the number of microplastics that we found in each filter, divided by the volume that the CANSAT went through. That way we have a maximum delta of 47.5 particles per cubic meter that is calculated with a minimum volume, and a minimum delta that is 18.5 particles per cubic meter. We can see that it is much higher than the outdoor hair fibers, as it is 0.3 and 1.5, and ours is somewhere in between 18.5 and 47.5. That way, since there is no contamination, as we know from the footage, and from the fact that the 9th and 10th filter have no particles at all, we can only speculate that the CANSAT has a high accuracy. So it captures much more particles than the research methods that were quite different from ours in both research papers in the lower part of the PowerPoint. Now we can see some of our samples. On the left we have microfibers, that little strings, and also microparticles. We are completely certain that microfibers are indeed microplastics, but we are not certain from the microparticles, as we need 1000 magnifyings to actually analyze it and see that they are microplastics. We can also see that there are some biological samples, a little piece of plant fiber, and a insect. So these are our samples, and we think that the secondary mission was quite successful.
Finally, we would like to thank you all, especially to ISA, A0, Ciência Viva and Governo Regional dos Açores for the opportunity of being here, and thank you all for this competition that was extremely compensating for us.
As I said, we had footage, both video and photographs of the landing, and the 9th and 10th filter had no particles at all. So if it was contaminated, everything was contaminated, as there were two filters with no particles at all, and we have the footage and photographs that the landing was very successful and the filter closed on itself. So the filters were protected by the parachute. We can be sure that there was no contamination. Now on the first part, our in correlation with the research done, it was they were very different methods. So they studied on the top of a building in Paris with vacuum pumps, and we did not. We had much bigger sample, but of course as the scientific method requires, we need to repeat this many times.
Make my final comment, which is your calculation of the total volume involved here is very uncertain, in the sense that you are assuming that the filters came in a cross-section perpendicular to the movement, and that was not the case as well. So the actual cross-section for the filter, something is if you drop like that, this is the area, something is if you drop like this, and the area is much smaller, you see? So probably the number of particles can be higher than the numbers you have there. And it's a very nice analysis. Congratulations for that. We could discuss even more, but our chairman would not allow me to do that. Thank you very much.
Did you design the parachute so that it would land closed? Because if not, you could never guarantee that there was not contamination with the soil. So how did you ensure that it would land closed, or was it by accident?
We were very lucky.
And furthermore, it was impossible for the parachute to land all the filters at the soil and all the filters be contaminated, because there was the can supporting them at least, or the parachute will be flipped it itself. So at least 1 filter, 2 filters, 3 filters will be available for analysis. And as we had the photographs of the landing, we knew the filters that were suitable for analysis and the ones that don't. And in this case, luckily, all the filters were available for analysis. Yes. We asked the organization for when they found our CanSat to photograph it, so we can know the filters that were good, the filters that were not.
Lucky is part of the
Yes.
so your secular mission saved your mission. So what
Yes.
is the lessons learned? Because I had the impression that you were not well prepared in terms of assembling the things to have the robust systems to send it for the mission. So what is your lessons learned in the global project?
First, yes, our secondary mission was a complete success. So what we learned. So we learned to have something that we can substitute if something goes wrong immediately, because we had like 5 minutes to do it. It failed 5 minutes before the launch, and if we had something more prepared, but it had to be an entire CanSat, as an entire substitute CanSat with a parachute and the filters and everything. It would be quite complicated. We didn't think about that. We had the component substitutes if we needed, and not the entire CanSat if something happened a little bit before the launch, and we had no time to substitute that.
This is exactly the point, because everything should be thinking about all the details of the project and also the contingencies. And it seems that because I also visit what you were doing before the launch, and I saw you are stressing to try to complete some things that you're not ready, so let's say, to fly.
Because yes, that was because Arduino was not working. It was working at that morning, but not in the tent for some reason. And yeah, it was like that. We had everything prepared, and when we went to the launch, it didn't work.
Okay, thank you very much.
Thank you.
Cheguem-se para. Deixa lá, chega não se põe atrás de mim.
Não,
vão para ali.
Isto esquerda.
Não, everything's okay. Good morning. Oh, okay, that's loud. We're up team. I'm Mariana, and in our team we have Luis, Emilcia, Jose, and Decilene. And today we're here to talk about our project that consists of two missions, obviously the primary mission and the secondary mission, and their results, respectively. First of all, we're going to talk about the primary mission.
For the primary mission, we built a satellite, we programmed it, and we measured the air temperature and the atmospheric pressure correctly. And we transmitted the data through telemetry to our ground station. Yes.
About the satellite, we have a problem because the button should be outside, should be inside. So when the parachute was released, it turned off the button. So we have big problem.
Okay, here we can see the results. Okay, during the ascent, it started measuring at ground level, obviously, because the satellite was on, and it started measuring on the ground, and the values during the ascent, and they gradually, well, obviously went up. We have temperature, air pressure, altitude, and methane, which is a part of our secondary mission. And it was, as we can see, we we reached 936 meters in altitude, and then we had that inconvenience where our can was turned off and we stopped having contact. But once it reached the ground again, we turned it on and it was working perfectly. So yeah, that was just a small issue. Small that mattered a lot, but
As you can see on the graph here, as the altitude went up, the temperature and the atmospheric pressure went down. But as you can see, it wasn't significant because the can was inside the plane when we got these values, so it didn't change a lot. We used a GSM antenna. It reached our possibility sent it. We probably were 1,400 meters away from the CanSat when it was launched, and we had a gain of 2.5 decibels.
The parachute performance was great. According to the standard requirements, was promote the satellite was totally safe.
yeah, it didn't have a single scratch, so that's a bonus. Yeah, here are the pictures when we got it. Yeah, the button was off, but but there were no scratches and everything was intact, so everything was working perfectly afterwards, so yeah. Now a little bit about the secondary mission.
So our goal was to measure the CH4 or methane in the atmosphere and compare them to various places, in three actually, in Santa Maria Island here, Lisboa and Santarém. All the results were different.
We meant to detect moving objects around the satellite during and after the fall with a Doppler radar sensor module. And we did indeed register values, which we're pretty sure it was the plane in movement because there was nothing around. So yeah, it could have been aliens, but I don't think they'd be this close to Earth. But yeah.
We use the power bank as a power source because I think it's not necessary. Right? And for SD card for Delta Lager. Okay.
Okay. And we saved all the data collected in an XLS file with PLXDAQ simple test, which is a software that, yeah, we used. Yeah. Okay. Sorry. We just wanted to conclude and say that the primary mission was successful, considering we were able to measure pressure, temperature, and all that. And yeah, the button thing didn't really go as planned, but it's something we have to improve, obviously, because it was outside the can. But yeah, we're gonna improve that next time, and we're gonna try to be better. And thank you so much for listening. Oh my God.
Well, let me stand up here in order to stress something. This is the first time I see, and previously has never happened, to have an antenna like this. You all have been trying used to Yagi antennas. They are complicated, they are extremely demanding in making the setup. This is an antenna that they put on the table, and they got all the data with no fuss. Really. Worked extremely well. This is a plus. I would say that from now on, everybody, every team for the future should think about this. This was really amazing, and I congratulate you for trying that.
Thank you.
Congratulations.
Thank you.
But don't forget one thing. To put this to work, you should turn it off.
Yeah. Yeah, we're gonna.
Let me, we are talking about antennas, and let me say something about this antenna. This is nice, and you will do the job for a short distance. If you have this in the real mission, for example, in the European competition mission, it will not work. Okay? It will not work because first you put a number on the screen, 2.5 dBs.
Yeah.
The gain. This means you are looking not only to your target, you are looking for all the islands. 2.5 dBs, 2.5 dBs of gain, is what this number means. You are not looking to the target. You are collecting all the things around you. So if the target is there, why you are collecting data from the back? So in the real competition with a rocket that's higher of 1.2 kilometers, I assure you that you cannot receive much. Here in this competition, well, it's different.
We did receive data from the furthest point where the plane, it was at its furthest point from our location, and we received data anyway. So that was pretty far away.
Yeah, but look, the mission is a completely sequence.
Okay.
Beginning to the end. And there's some range variation, change during the mission.
Mhm.
And you should assure every second to receive your telemetry. This is what will define the success of the mission. Not only your project, but all the projects.
Okay.
The ground segment is the way you are assuring the success of the mission. You can have very nice primary mission, secondary mission, but if you don't receive the data, this is what happens in the real mission. We have a billion satellite or million satellite cost of satellite flying in the orbit the Earth. If you don't receive the data,
Okay.
you don't get them.
Mhm.
I would like to say something about the antenna, not only for you, because I think I already said that to you, but
Yeah.
For everybody else. It's quite important when you use something like the antenna to know what you are using, to characterize what are you using. If you're using a GSM antenna, that's actually for a different frequency. good antenna. Anything can work. We had a team with a wire that almost received the data with just a wire, nothing more. So anything can work as an antenna. And 2 dBs, if you ask the other teams with the Yabbies have a proven gain of 9 dBs, 8, 9 dBs. And 2 dBs is not much. But you say you have 2 dBs because that's the specification of the antenna. But that's a specification for GSM frequencies. It's different from the frequency that you are using. So you have not characterized the antenna you are using. You don't know even if it has 2 dBs. You could use it. You can use anything, as I said. But you should characterize it. And that would give you some safety about the mission. You did something that's also very good and very important. You went onto the field and you tested on distance and you said you have obstacles on the middle and everything. And that is great because you can have everything working on theory, like an antenna with 9 dB, and you cannot get anything on the practice. So it's good to associate both of them, the theory and the practice. So that's a suggestion.
Let me say something, complement what is said. Don't forget one thing. If we are talking about 3, the number 3 dB, that means simple, the double. 3 dBs means the double. That means you are, if you lose 3 dBs, you are losing the double of the power, the density that you are receiving. Talking about distance, we really don't mix the things, but you are losing 4 times the distance. You see? So having 2 dBs or 5 dBs or 4 dBs is completely different in terms of the range that you can achieve the sound. That's the reason I told you that in the real mission with the rockets, it will not work. Okay, and the different of references. Okay.
Okay, thank you very much.
Thank you.
Yes. Good morning, everyone. We are the Almeida Set team, and we are going to present our final report. Basically, other from the primary mission, we also had a secondary mission. This was detecting fire focuses through our satellite through an infrared camera. We decided to do that because simply of last year's catastrophe. As we all know, there were many fires last year that devastated all the country, destroyed infrastructures, and even take lives away. We wanted to prevent that because it's really important to preserve nature and humans. So, to do that, we used an infrared camera, as I said, to detect heat sources.
Our satellite had a Raspberry Pi Zero, as well as a battery, an infrared camera, also a database that stored data in an SD card, and also an antenna connected to a transceiver. The ground station had a Raspberry Pi and also an antenna and a database. So we had two databases, which was very helpful for us, since we didn't have we couldn't get the satellite to communicate with us while we were in the ground station. We also used an SDR dongle to verify if there was any data transfer. We had difficulties in managing the time because the execution was really difficult for us, since we are in the 11th grade and we don't have much time. Also, in the data reception, as I said previously, because we couldn't get many data, we could get data in the beginning, but we couldn't get throughout all the fall. And in recovering the satellite, since it took a lot of time for us to recover it, even though we had a buzzer and also the color of our parachute was really bright, it was orange. To improve our satellite, we could use a GPS device to detect exactly where the fire was focused if we find a heat source. Lack of telemetry, as I already said, due to the connections, they were weak, so we couldn't get many data. And lack of time, as I already said. Also, we could implement a real-time clock. That would help us to detect even faster where the fires were. So a team, for example, of firefighters could act really quickly. These are the results we got. So the first graphic is barometric altitude, and the first point is negative, and I'm going to explain why. Simply because there is pressure determined for each altitude, and we took the barometric altitude from the satellite. The satellite, from the pressure that was in the spot, told us that the altitude was negative. Even if it wasn't, this is the data we could recover from the satellite. As we can see, I think, from our graphics, all the data are correct or nearly correct. We can see that approximately at 300 seconds, there was the fall from the plane. And we calculate velocity, dividing the altitude and the time of the fall. The barometric pressure graphic shows us that when the altitude goes up, the pressure goes down. They are very accurate data, and we also can see where the satellite was dropped in the graphic, which is here. We also have the same previous graphic here because we wanted to compare both, and this is the temperature graphic, which is also very accurate, despite these dots here that are really dispersed. But this, the reason we think this happened was because our sensors were outside the can. So what happened can be, for example, any condition variation, a wind, or even due to the sunlight when the satellite turned. It can create a really dispersed temperature data. We also can see exactly the spot where the satellite was dropped. That's here. That's why there is a really big gap between both points, because the satellite was inside a plane with a certain temperature, and when it hit the air was a lot colder than inside the plane. So there was a really big crash in the temperature and the time the satellite was dropped. As far as it comes to our secondary mission, we have here some results. We used the infrared camera, and as we can see, it worked. So we have in the various pictures bright areas that that are heat sources, and the dark areas which are more cold spots. We have a issue that can be, I think, worked out. That's we can't distinguish fires from other heat sources right now. That's due to the technology. We don't have the technology necessary to do that, but this can be really worked on, I think. Here we are some pictures to show that we also could really know what's in a photograph. So to conclude, we think that our primary mission worked out. Despite the lack of telemetry, we had a backup system. So we had an SD card in the satellite and we could storage every data. And as we recovered the satellite, we had all the data we needed to construct our graphics. I think the data are really accurate within the satellites we had. And I also think our secondary mission was really successful, since we were able to take more than 300 photos throughout the fall. As you can see, and the camera works, and it takes pictures from 10 to 10 seconds. We thank all of the organization and institutions that made this happen, and we also wanted to thank our teacher, our sponsors, and everyone in this room. Thank you very much.
Congratulations for your nice presentation. I would like to just ask a short question. All your data were retrieved from the SD card?
No, we had data, but it was only in the beginning when the satellite was in the plane, but we couldn't get many data from the fall. That's why we had a backup system that worked, I think. So we recovered the data from the fall from the SD card, but the other data we could really recover directly from the satellite. Yes, it was a Yagi antenna set for 433 megahertz. Yes.
Just a question. Can you go to the temperature values?
Yes.
You have? Okay. You have there some of the best temperature values that I've seen, because there are actually very fast. Most of the temperature sensors are inside the cap, and you don't actually measure anything because the time to establish thermal equilibrium is too large. And this really shows some useful temperature data for the first time, I think, in a lot of downside competitions. One of the first that I've seen. It's really, really fast to establish the temperature. You have another issue there, and it's not an issue. It's actually very correct. Which value did you calibrate the pressure, the barometric pressure for the zero? Which value did you use?
So basically, we used altitude. The value of the altitude was minus 41 due to the pressure on the scene.
Okay, but which pressure, which reference pressure did you use?
Which reference?
Yes, the reference pressure. You have to compare some reference to say which is the level zero. Which reference did you use?
I think we used the level 0 pressure reference.
Okay, I have, let me emphasize that the temperature measurements are very good. You should have stressed that even more, because it is necessary to put the sensor outside the can in order to be able to measure something like that. The fluctuations, it's not a problem. You have a trend. When the can was dropped, the temperature was lower, and then it started increasing. When the can hit the ground, then it started warming up again, and you see the continuous curve over there.
Yes, because it was black, so it was receiving radiation. Yeah.
Exactly that. So the temperature values are good. The part that you were missing here is to give us the number of
The drop speed, sorry. Yeah, it was 12 meters per second.
12 meters per
Yeah.
second. Calculated, how did you calculate that?
We divided the altitude through the time fall.
Okay, the correct way would be to do a linear fit to the values you have there. That would be the perfect way of doing that. Okay, so you had very nice data. I would expect you to do much better, but congratulations for the result. You had the SD card, so comms were not working very nicely, but you did get some data.
Yes.
My final comment is about the infrared pictures. Show us the infrared pictures. I would like, when you present that, would be very nice to explain to the audience how would you be able to interpret and get some conclusions out of that. I mean, where is the ocean? Where is the land? Where is me?
So,
just a black and white picture or
yes.
picture is not enough.
Due to the colors, I mean, it's really contrasted, the images. We don't really know what thing is which yet, because we only did one drop, so we don't have data to study it enough. So we can know what color represents which, for example, material. So we assume that the brighter colors are the...
Therefore, what is the usefulness of this?
Well, it has to be improved, because we need to have higher resolution and better camera.
Not just resolution, but congratulations.
Thank you.
Where are the team of Serra da Estrela?
És tu, isso és tu, isso és tu, não és, não sou eu.
The journey of Kansat is the little point. The scream represents the flying of the mission Kansat.
This is data accretion follow chart. Everything well, until Kansat placed on the board. We lose communication during takeoff. The backup is secured CD card that recover flying data.
These theoretical results prove the tests carried out Serra da Estrela 200 meters.
So, as you can see, our land just got burned, and we lost half of the Serra da Estrela, and that's why our secondary mission is reforest the lands. Okay. Pause. Initially, we created this secondary mission to colonize another planet, but it's a little bit difficult. We don't have that skills, so we create a mechanism that will spin and will spread seeds in the lands. So during the flies and when that collides with the lands, that will grow and that will reforest the lands.
We test a new type or parachute and power supply. We test our parachute and wind tunnel. We compile the information of CANSAT with a new layout. Thank you all for the mission.
Não, fica tentando saber, não quero.
I will make you let's say a remark. The first presentation that you did yesterday to us, we give you some, let's say, some recommendations to try to focus on the main point, and you are fine. You have, we notice that you have difficulty to express yourself in English, but there are at least one or two that can do it. So you should probably concentrate in this person that can explain at least the main achievements of your project. The primary mission, the second mission. So to try to at least to explain us and to the audience the basic things that you achieved. First question: Did you were well succeeded in your primary mission? You received data.
Ele está a perguntar se foram bem sucedidos. Se foram bem sucedidos. We lost some data. And all. All. Basically.
And your second mission, it was also well succeeded, also with
Yeah, that's succeed. It worked.
It was not well succeeded.
No, this succeed. It worked because we try in some lands that was burned, so that grow. And yeah.
Did you release any seeds?
Yeah.
Yes?
Mm.
So that is a success.
Yes.
And did you get your energy panels to function? Solar panels.
Yeah, we try to put them to work, and they work a bit.
So they work.
Yeah, man.
Did you register the data in an SD card or no?
We lost the SD card in the collusion with the land. In the collusion.
Last question from the right. Not a question. It's just I would like to highlight this way to show the graphics. It's really nice. You have very good drawings and schemes.
Thank you.
It's very good. I would like to highlight something of
solar panel, most times that is used is useless because the power provided is very small. They use it to power up a LED, a light emitting diode, and they studied the light emitting diode. So everything they did was great. However, you do not transmit the work that you do. You fail to transmit, and if you fail to transmit the work that you do, we cannot see it, and you cannot be recognized by the great work that you did. You should be proud of the work that you did. You should show the work you did with pride and raise your head because you did a really nice job. Okay?
Thank you.
Okay.
Como é que tu passas para o próximo slide? Mostra-me lá.
Tem que ser no teclado.
Tem que ser no teclado, não dá para
Querem
filmar.
primeiro o vídeo ou primeiro a apresentação?
Não, é a apresentação primeiro.
Podemos abrir o vídeo já. Será que. Depois. Isto aqui está.
Tá? Um, dois, um. Tá, está a funcionar. Ah, ok, tem que ser aqui. Sim. Preparados? Good morning, ladies and gentlemen. We are the team Procyon. Passa a slide. And our mission is to send a living being into a non-specific planet, while recording its behavior through the fall. Parallel to that, we will be also receiving data that is the percentage of O2 in the atmosphere, the UV intensity, the pressure, the temperature, and the humidity. All of this so that we can conclude I'm sorry, my English is a bit bad right now. All of this in order to conclude if the planet is habitable or not.
Using having pressure and temperature, we were able to reach the altitude, and giving altitude by function of time, we had velocity, that was the slope of the graph. So we could determine it, what was indeed the terminal velocity of our parachute. And I must say, it was a success. It was a success. I was afraid it wouldn't work, and after the first day when we tested, the cards get tangled, but I was able to solve it, the team was able to solve it, and it was a success. But further tests in another project we'll have to improve, because it could get more stable. As well as our casing. The hexagonal perforation should have different rotations for the fractal plane to be different, so it wouldn't actually broke, but it did broke, but it was okay because our cockroach was safe.
Now I will talk about the temperature, pressure, and the humidity gradients. These graphs are all about the fall. It's only during the fall time that you start. Here you can see in the right the expected results, and on the left we have the results that were obtained. On the temperature gradient, you can see that here the trend line, the main line, is really close to the one on the expected results. For the pressure gradient, you can see that